So, why is gravitational potential energy always negative? This is a problem that a lot of people have in intro physics because it's kind of confusing with intuition. Why would potential energy be negative, especially for a situation like this, or even in electrostatics where the sign kind of depends on the signs of the charges. So, to start, we're going to say there's a big planet right here, big M, and it's being attracted to a little moon over here, which is being attracted back. And we know this is attracted by the force of gravity, which is F equals big G, constant of proportionality, times M over R squared. And if we're going to talk about when this force would be zero, that's only true when R equals infinity. When this mass or this mass are infinitely apart, there will be no attraction. So this is going to be how we start to define our potential energy. It's that the system can affect the masses less the further apart they are. So what we can do, similar to the work definition, but we'll show the difference in a second. To get potential energy U, we're going to do the integral of the force of gravity. And we'll talk about the bounds in a second, but we're going to integrate, because if you know force is a Newton or a kilogram meter per second squared, and then potential is a joule or kilogram meter squared per second squared. So to do that, we need to integrate with respect to distance. So we'll have Gm over R squared dr. And that's a dot product because our result for potential is a scalar quantity and force was a vector quantity. So now, our bounds for the integral, we are going to say that the potential is going to be zero at R equals infinity, which means that our lower bound is going to be infinity. And then our upper bound, well, we want to know this for any R, so our upper bound is going to be R. And then if we compute this, you're going to find that this integral comes out to negative. And at first I should say, if you ever want to swap bounds, you can put a negative, and then the bounds will change sides. R to infinity, if that's more comfortable. It's weird having infinity on the bottom bound, but just work with it. Then you do this, Gm over R squared dot dr. Your answer is actually going to be negative Gm over R. And this is what people say the potential of gravity, potential energy. And this is consistent with the further definition for potential energy, which is that force equals the minus gradient of potential energy. And gradient in this sense is going to be, I think it's a little, I need to move it down. Gradient is a spatial derivative operator. So this, if in our system, what we're talking about, this just means d over dr. But these would be partial derivatives. It's nothing to worry about if you're just in intro physics. But anyway, what this just means is that force equals the minus derivative with respect to distance of the potential energy function. And we can move this back around to do the integral, the negative integral of force dr equals potential. And again, the bounds, the bounds are dependent on your scenario. So if we stop, let's go to electrostatics. So for an energy total, there's always the kinetic component K plus U, which is the potential. So how do we use this? So K would have a velocity component, 1/2 mv squared, and you can get relativistic if you want, but it doesn't really matter. U is potential, which we just talked about for gravity. But what if we're doing electrostatics? So if there's a charge right here, Q1, and it's flying this way, and there's another charge over here, Q2, and we'll say Q1 is positive, and Q2 is also positive, and we'll say, we can use charges later, but this one's moving and this one is stationary. So you would think there's a magnetic force component here, but it actually doesn't matter for the energy components because magnetic force does no work. So the kinetic component of energy total would still have to do with this one's velocity in the system, but the potential, there's no magnetic potential energy because you can do no work. So if we start back with our force, we know that the force of electrostatic force is proportional by 1/epsilon naught 4 pi or KEQ or KE, and it's proportional to charge 1 times charge 2 over the over the distance squared between them. And this looks very similar to the gravitational equation, except that the forces are a little differently defined because this equation has no clue what the charge magnitude is on these, and the charges can be negative, unlike mass. So actually a better fit for this equation would be negative. So what I just did was when charges are positive, they're going to repel each other. So when Q1 and Q2 have no signs, if they're just positive, then this equation will produce a negative force. And we're talking about a defined coordinate between them, R. If we're locking this one in place, there would be a negative force. It would be going in the negative R direction. So now we can say that if the charges were negative and then positive, this minus sign would vanish and they would be attracted together. So we start and go through the same exact process. The integral of minus K E Q1 Q2, which are the charges over the distance squared. This is going to be equal there's a dot dr there, and this will be equal to the potential, the electrostatic potential. So what are our bounds? Again, we need to talk about a situation where the potential would be 0, because we want our lower bound to have a potential of 0. So, well, same deal. At r equals infinity, the charges will not interact with each other. They can't feel each other's repulsion or attraction, because in this scenario there can be either. So put r equals infinity on the bottom. Again, we wanted to integrate to a generic r. And this could get a little weird with indefinite integrals. I'm using the same r, you're supposed to use a different one, doesn't matter. So now, like I said, you could flip the sign on the integral if you swap the bounds, which would cancel this sign, so it actually would be just the regular integral KE Q1 Q2 over r squared dr. And this comes out to KE Q1 Q2 over r. Notice that this is positive. This is when it's defined that an attraction, which would be Q1, is the opposite sign of Q2. This would be a negative quantity. Again, negative potential energy, which is kind of weird. So now let's talk a little bit about what happens in the system. So if the charges, let's just say they're equal charges, equals negative Q1 equals negative Q2, and in that scenario, we would end up with, let's go back to energy total real quick, hold on a second. K, which doesn't really matter, like I said, because there's no magnetic potential. We could add a K, it doesn't matter. Let's just forget about that. Let's work on potential. And because this would be a negative quantity, it would be minus K E Q1 squared, because we set it equal over R. And what this does is as R increases, this number gets closer to zero. So the energy of the system is subject to R, which is why this looks kind of weird. So as the charges are pulled further apart by some means, some work, this potential energy will go down, and that's why, or sorry, it'll go closer to zero, up to zero, which is weird. So if it equals zero, they're infinitely far apart. We know this. If they get close to zero, they're getting very far apart. So the energy is actually of the system. This has no meaning on that energy anymore. It's falling off. And then if they're very close, this is being subtracted to it, but you have to think about it as a magnitude. It's part of the reason why the total energy of a system can be negative. So that holds true for gravity and electrostatics. There will be more videos soon.